Okay, all right. So this is our class 2 to solve assignment for the week 2. So here what we'll do is that again we have 10 questions. So let us start solving them. Now the first question is, a particle of mass m is confined to move in a potential of the form Vx equal to 0 when it is between x from 0 to a, and it is infinite otherwise. So from the shape of the potential, from the structure of the potential, functional form of the potential, you can guess that it is like an infinite potential well problem, or in other words it is a particle in a one-dimensional box problem, because the potential is only 0 within a box of size a from 0 to a. Here the potential is 0, and all the other spots like outside this box, this potential is infinity. That means it is an infinite potential well, or it is particle in a one-dimensional box problem, right? So now it is saying that the wave function of the particle at time t equal to 0 is given by this. Now what should be the normalized wave function can be written as? So you can see in this wave functional form there is this a, which is an unknown constant here because they have not specified any value of a. Now you know that any wave function, to be it physically valid, it has to be satisfying the normalization condition. So going by that, a normalization condition must be satisfied for it to be a valid wave function, and once you apply the normalization condition on this functional form of psi, you will get what the like form of the constant term a will be like, and you will get an answer one of this out of one is on one of these four options. So the answer to this question is that we have to simply apply the normalization rule of wave function. So to normalize the given wave function is psi x comma 0 equal to a sine 5 pi x by a cos 2 pi x by a. This is at t equal to 0 because this is the psi x comma 0. Now applying the normalization condition means you have to integrate psi x whole mod squared dx to be equal to 1. So it means that now psi x whole mod square means psi star into psi. Psi star is the complex conjugate form of the wave function psi, but because this is a totally real functional form of psi x, so anything that comes out of it will be real, because sine some argument of x will not be a complex quantity. So what you get is this constant a whole mod square out of this, and you put the other terms as it is, right? And also look at this integral limit. Now we'll be only solving the integral limit from 0 to a and not from minus infinity to plus infinity. The reason is simple, because the particle can only exist within the potential well where the potential is 0. Psi not equal to 0 only where v equal to 0. But where the potential is infinity, there the particle itself cannot exist because the particle cannot go there, right? So, and psi equal to 0 where v goes to infinity. That means psi is equal to 0 at everywhere except from 0 to a. Except from the box, you can say that box has a size of a. So except from 0 to everywhere it is 0. That means it does not make sense to take the integral from minus infinity to plus infinity. So we'll only take from 0 to a, and then it is sine square 5 pi x by a cos squared 2 pi x by a dx equal to 1. Now one thing to make clear out here is that you can reconstruct this functional form of psi so that it it makes it easier for you to integrate out. So like you can express psi x comma 0 equal to, so it is a product of sine something and cos something. So it is, let's say, a product of sine a cos b. So you know that 2 sin a cos b equal to sin a plus, sorry, I need to construct it otherwise. So you know that there is a sine cosine rule or product rule formula where it says that sin a, I'll not call it a because you can confuse it with this a. So let's say sin alpha, it's an argument, and sin beta another argument, is equal to 2 sin alpha plus beta by 2 and cos alpha minus beta by 2. So you can convert a summation of sines into product of sine and cosine, right? So here in this form given to you, you can see that the sine has this alpha plus beta by 2, which is given as 5 pi x by a, and the cos has alpha minus beta by 2, which is 2 pi x by a. So from this you can guess that alpha plus beta plus alpha minus beta, so you basically add these two and you take the 2 to the other side, multiplied on the other side, so it is 10 pi x by a plus 4 pi x by a. Now this beta and beta cancels out, so this 2 alpha is equal to 14 pi x by a, or alpha equal to simply 7 pi x by a. Now if you have got alpha already, so beta is simply 10 pi x by a minus alpha, so it is 10 pi x by a minus alpha, and alpha is 7 pi x by a, so it is simply 3 pi x by a. So from there you can write it down that this product form is actually half of this sine alpha plus sine beta. So you can express this a sine product of sine and cosine as a by 2 using this formula, remember, using this formula. And you have already calculated from this what alpha and beta should be. So you just replace this formula directly here. Only this 2 term will be coming towards this left side as a half. So this is a by 2 from that half into sine alpha is 7 pi x by a and sine beta is 3 pi x by a. Now once you have done this, we have separated into from a product form to a much simpler summation discrete form. So now integration would be easier, that 0 to a, now a whole mod square, so you take a whole mod square of this form, so a whole mod square by 4 into, this is sine square pi x by a plus sine square 3 pi x by a dx equals to 1. Now you do the usual integration and step by step, slowly and carefully. So you assume that a is a real quantity, so let's take a whole mod square as a square and take a square by 4 as constant, so out of the integration. And so sine squared is how to sorry, I did a mistake out here. So the problem is that this is not individual terms square, but it is the whole square, right? Yeah, so this is the whole square. Why? Because you are taking this whole thing whole square. So even if in the earlier form I did the mistake because it was in the product form, so you can separately take the square on the individual products, but for a summation thing you cannot do that. So better take a whole square out of this condition, and this whole square when is expressed from a product form to a summation form, so it makes a whole summation whole square. So this is basically, now you a plus b whole square, you apply the formula. So this is sine square pi x 7 pi x by a plus sine square 3 pi x by a plus 2ab is 2 sine 7 pi x by a sine 3 pi x by a dx from 0 to a equal to 1. Now you may think that okay, you have to solve the whole integral, but actually this makes your life pretty simple, because you know that sine squared or cos squared, these kind of oscillating functions with their argument, let's say in this case the argument is y, when you take an like expectation value or average of them, you get half, given the integration limit is from 0 to 1. But in any other limit, let's say 0 to a and sine squared y dy, you will get a by 2. Okay, so the whole period that it covers by 2. So basically this integral of sine square will give you uh, a by 2 directly. Similarly, this is also a sine square, so it will give you a by 2, because remember the integration limit is from 0 to a. So I can, maybe this is not necessary to show, but let's say for your convenience, let us take one example and how this is coming a by 2. So let us say y equal to 7 pi x by a. So dy equal to a by 7 pi dx. Now if x is from 0 to a, then y will be from 0 to 7 pi a by a, which is just 0 to 7 pi. So this whole integral modified to sine square 7 pi x by a into dx is 0 to, so this was just an example, so let us take it out of the equation. So 0 to, now y's new limit is 7 pi, and the sine square 7 pi x by a, so you redefined as y, this is sine squared y, and dx we had to redefine as 7 pi by a dy, right? So this is, now if you go by usual standard form of how to solve this integral, then let us take the constant term out, and you know that sine square theta is 1 by 2 1 minus cos 2 theta. So this is 1 by 2 taken out, and 1 minus cos 2 theta is 1 minus cos 2y dy. Now this is 7 pi by twice a into this integral, first giving you y, minus cos integral is sine by 2y, so it is by 2 from 7 pi to 0. Now because sine 0 is 0 and sine some integer multiple of pi is also 0, so this whole term from this integral limit will give you only 0, except for the first term which gives you 7 pi minus 0, that is 7 pi. Sorry, that's why I was thinking that why the factors were not matching quite. So basically this is dy equal to 7 pi by a dx. So when you do this and change the limit, change the dx into dy form, so this is not 7 pi by a, but this is a by 7 pi. So pardon my mistake, so just a little, I just messed up with the terms, but please correct this, that this is now dx equal to a by 7 pi dy. So this is a by 7 pi, and this is when you take the half factored out, so there will be another 2, right? This is a by 14 pi. This is a by 14 pi. So you see pi and pi cancels out, 7 and 14 it's 2. So this is a by 2. So I have proven to you that indeed this first integral, when you have a sine square and the integration limit is from 0 to a, so you take the upper limit of the integral and the answer will be that integral upper limit by 2. That is the rule. Once you know this, that you will see that the integral involving sine square terms will be much easier to do. So the first term will give you, first term from the integral gives you a by 2. Similarly, the second term, only the argument is different. Instead of 7 pi x by a, it is 3 pi x by a. But eventually, if you solve by this, you will see that that does not matter, that whether you have a different integral multiple in the argument. But what matters is that you again have the same upper limit a. So it is again a by 2. Now comes the term where you have two different sign with two different arguments. You cannot really say this is a sine square term, right? Because for it to be a sine squared, it has to be it had to be similar arguments, but it had different arguments. So you have to take each of them separately. And if you do that, if you take integral by parts, so you'll see that you have to deal with individual sine components and not a sine squared component. And it is also a well-known rule that if you have individual sine in an integral with this integral upper limit as the full period of that sine, so then the answer will be 0. Okay. So this part separately will give you 0 and this part will separately also give you 0. So I can show you that here briefly. Let's see, you have sine. So basically you have to apply integral by parts, or you can like again make it more simpler, that you can apply this product to summation conversion rule. I think there is a rule that relates this products of sine into summation of cosines, if I remember. So you can do that and eventually you'll get a cosine alpha plus cosine beta sort of a discrete forms, and then you take integral on each of these individual terms and you'll get either, if it is cos in the integral, so you will get a sine 0 to some limit that changes this integral integrand from x to y. So this will be like sine, right? And anything that has this thing from lower limit to the upper limit of something multiplied by pi, sine will always give you 0, right? Similarly, even if you had it instead of cos, if you had it sine and the total integral period is taken, so from the integration you would get cos, right? Cos from 0 to this thing. So it depends whether this pi multiplied with this coefficient is an even or an odd term, because you know that cos of 0 is plus 1 and cos of any even multiple of pi is plus 1, but for cos of any odd multiple of pi is minus 1. Like say cos pi is minus 1, cos 3 pi is minus 1, okay, 5 pi is minus 1, like that. And here in this case you can have cos 2n pi. I am just writing 2n just to signify that it's an even number always, no matter what. So let's say it can be 0 as an even number, then 2, 4, 6, I think all these are known to you, so this will be plus 1. So depending on that, it can be like either 0 or can be minus 2, right? But in our case, because we have two sign in a product, so you'll get cos in terms under this integral, and cos integral will give you sine, which is basically under this whole period give you 0. So that is our answer. That very quickly we get the integral result as a squared by 4. The first integral from 0 to is a by 2, then the second integral is also a by 2, third integral is 0. So this is whole thing is equal to 1. So then it is a squared by 4 into a equal to 1. So this a is equal to 4 by a square root is equal to 2 by root over a. Now once you have gotten the integral constant or integral this a constant value, so then you put a here. But you can see the answers, if you look back to the options given to you, they are not in the product form, but they are in the summation form. So clearly the summation rule that we have used here to simplify our integral has to be involved. It has to be involved in the final form. So basically you use this form instead, and you put a as a by capital A as small a by root over 2. So the whole thing is a by 2 root over 2. Then sine 7 pi x by a plus sine 3 pi x by a. So this is your final answer. So sorry, I again have messed up. So this is 2 by root over of a. So sorry. So this is 2 by root over of a. So this 2 comes on top and not at the bottom. So my mistake. So let us redo it. Okay. Someplace else, because it is getting too congested here. This is a by 2 sine 5 pi x by a plus 3 pi x by a, remember. So our final answer is we got already from summation to product rule in conversion, that it's a by 2 sine 7 pi x by a plus sine 3 pi x by a. And from our calculation we have gotten that capital A is equal to 2 by root over small a. This is 2 by root over of small a. So when you put this out here, so this 2 and 2 cancels out. This is only 1 by root over of a, this sine. So our final answer will be psi x comma 0 is 1 by root over of a sine 7 pi x by a plus sine 3 pi x by a. So this is our answer. So hopefully you have gotten the answer out of these options. So you can see our answer is this one. This is the correct answer. Now for question 2, for a harmonic oscillator in a ground state with wave function psi naught x this is a known wave function if you have solved the harmonic oscillator problem of quantum mechanics. So this is the generically known form of how the functional form will look like. Yeah. So this is psi naught x because they are talking about the ground state of this wave function. Psi naught means it is the ground state, and the form is also for the ground state of the wave function. And the probability density is maximum at x equal to 0. You have to say that is true or false. So one thing that comes to your mind, that whatever the wave function be given to you, may it be a harmonic oscillator wave function, may it be a different wave function from a different physics, but the idea is that you have to find out whether the probability density is maximum at some point. So first of all, you have learned about the probability density, how to get that if you have the wave function, right? So probability density is nothing but the whole mod squared of the wave function psi that is given to you. So let's say you have psi as the wave function. It can be a complex wave function, right? So the probability density is simply, sometimes people in the book, they mention this probability density as J also. So in this case, because it is a one-dimensional case, so it is only be a function of x, because psi naught is also only a function of x. Jx is the probability density, that is basically psi naught x whole mod squared. So that is the idea, or that is the formula, expression, whatever you say, for probability density of a quantum mechanical wave function. And just for an additional information, because you have probability density, so how to get probability is basically integrate on top of that. So because it is a one-dimensional case, so density generally you can correspond generally to be in a 3D model, like when you have volume and mass. So basically mass by volume is your density. So when you multiply density by into your volume, so you get mass back, right? But in this case, because it is a one-dimensional case, so instead of a volume, you only have length. And probability density, when you multiply it with the length or integrate it basically, because it is a continuous variable, not a discrete case. So the total probability is just a integral of this density probability into dx, to whatever be the extent of the wave function. Initially we can take from minus infinity to plus infinity, and then depending on how psi naught x is there and how the potential looking like, you can choose the limit. But the idea is that this is the probability density expression, and you have the expression of psi naught x given, and from there you have to find out whether that function has a maxima at x equal to 0. So pretty simple, the idea of this problem. So now let us get to solving it actually. So this number 2 is psi naught x is the ground state wave function for the simple harmonic oscillator case. So this is m omega by pi h car to the power 1/4 exponential of minus m omega x squared by 2h car. Now the probability density, we call it now px for our convenience. This is psi naught x whole mod squared. So basically because this whole term is real, not complex, so this is the direct whole square of it. So m omega by pi h car to the power 1/4 whole square means this is 1/2, and this is exponential of minus m omega x squared by 2h car into 2, because e to the power x when it you e to the power y when you take the whole square of that, it is basically e to the power of 2y. So this 2 is from there and this cancels out with this. So this is the probability density expression. Now the condition for any function to be maxima at some point is that to have a maxima at random point, let's say x equal to r, is that that function's derivatives, first order derivative with respect to the dependent variable, in this case x, has to be 0 at that particular point that you are asking about. So this, let's say at x equal to r, dp by dx will have to be 0, and not only that is sufficient, because that is a condition for both maxima and minima, that is a common condition. But what takes us to the next step, that for it to be a maxima and not a minima, is that the second order derivative d2p by dx2, which basically indicates physically the curvature of the wave function, curvature of the functional form. So that second order derivative at x equal to the same point r has to be less than 0. So basically there can be problems, or there can be questions where you may have been asked about whether a point is a minima for a function. So in that case the approach will be pretty similar. Only thing is that instead of maxima you have to apply the minima condition. So this condition here, out here, will be same for both maxima, same for both maxima and minima, in short. But for minima there will be the second order derivative condition will be different. So first you have to satisfy this, and then when it is satisfied you move on to check this. So this is the first step and this is the second step. So, and for minima is that if x equal to r holds a minimum for this function, then this curvature or the second order derivative will be greater than 0 for minima. So for this functional form of px given to us, we have to first calculate this first order derivative. We check that this is equal to 0, and from that information we move on and take the second order derivative and check whether it is less than 0. Then we'll be saying that this is maximum. So in this case r equal to 0. So they are asking us to find out about x equal to 0, but that position is actually for this function px. So if that is a px formula, you can see, you can take the derivative. So dp dx equal to, the constant term remains as it is. Exponential of this thing is basically the power of minus m omega x squared by h cut to minus m omega 2x by h cut. So this whole thing is equal to 0 because dp by dx has to be 0. Now here you can see, ignoring the constant terms, that will be anyway ignored because they cannot be 0. So only term involving x is that x into e to the power of minus m omega x squared by h cut equal to 0. So from these two roots are possible. The simplest root that can be satisfying this equation is that x equal to 0 is one possible root, right, to satisfy this. And this satisfies your first common condition, dp dx equal to 0 at x equal to 0. This is true. But to confirm further whether at x equal to 0 is a maxima, so you have to take the second order derivative, that is d2p by dx2 equal to, you start from here, and this is m omega by pi h cut to the power of half minus m omega, 2m omega by h cut into x time, this thing has to be taken derivative over all over again. So this is on x first, so derivative by parts, or sorry, it is not derivative but by parts, it is, I think, whatever, the term by term derivative. So so this is 1 times e to the power of minus m omega x squared by h cut plus x minus m omega by h cut into 2x into e to the power of minus m omega x squared by h cut. So this is, you take this thing common, this is not plus, this is product. So you have now m omega by pi h cut to the power of half 2m omega by h cut. So you take this minus sign within and you take this common term out. This is minus e to the power minus m omega x squared by h cut. The first term is minus 1 because you take this minus 1 in, and the second term has already minus, so this minus and minus makes it plus. So this is 2m omega by h cut x squared, sorry, this thing has been taken common out. Now if you place your x equal to 0 here at x equal to 0, so this term goes to as 0, and this is minus 1, that is coefficient for the whole other rest of the term. So this is negative, you can see. That means d2p by dx2 is less than 0. That means x equal to 0 is a point where the maxima lies for this function of the probability density px. So finally we get that our answer is yes, it is true that x equal to 0 is a maxima. This is true. Now question number 3 is, a particle of mass m is trapped in the potential Vx equal to 0 from minus a to plus a and equal to infinity otherwise. So this is kind of a box, but the box size is not a but 2a because it is from minus a to plus a. And everywhere else the infinite potential is there. That means particle cannot exist except for this place. Now the probability of finding the trapped particle between 0 to a by n when it is in the nth state is 1 by n. So that is a statement they have made, and they have asked you to say whether that is a true statement or false. So basically you have this whole white box. From 0 is the center, so this is minus a to plus a is the box's size, and the particle can be anywhere within this size, but everywhere else, because the potential is infinity, only here it is 0, so it can be anywhere here, but it cannot be anywhere outer than this. So for that thing is we are clear. Now between 0, that is this point, to some positive x, let's say x equal to a by n, that means 1 by nth time this whole extent a. So somewhere between this position you have to find the probability of the particle lying or being trapped. When the particle state has been defined to be the nth state for this case. So this is basically the nth state for this infinite potential well problem, and you have to find out the probability, not probability density. So just in the last case I told you that probability is psi whole mod squared, but the probability density is psi whole mod squared, but probability is the integral over that, because that is the total summation or the compilation of all probability densities over the entire length, because it is on one dimensional case. So that is what we are going to do right now. We will be using the, first of all you have to know what is psi for this case of this particle. Then we have to take the probability density, and from there we have to get the probability by integral, and then we have to get what is the value of that probability within the integral limit from 0 to a by n, because that is the extent up to which the particle being trapped is what you are asked to find out the probability of. So we draw this potential, infinite potential well again. So this is from minus a to plus a, and anywhere else it is infinity potential, so the particle cannot exist there, only here it is 0. So now if this is the center of the well, and let's say this is another point where you have drawn a by n, and you have to find the probability of particle getting trapped anywhere in this region. Now for doing that you have to get the wave function of the particle, and because it is a 1D box problem, you have to identify the problem eventually to directly get the answer. So this is a one-dimensional box problem or infinite potential well problem. So you know the wave function for this case generically, that is psi n x equal to root over of 2 by a sine n pi x by a. Right. Uh, so I think there was a correction to one of those problem sets, if I remember correctly. Let me just check whether this was the problem set or not. Okay, so just let me check and continue in a bit. Okay, sorry, that was a confusion, so I have cleared it. So anyway, let's continue with what we were solving. So this is fine. So this is, sorry, this is the wave function for infinite potential well kind of a thing, where this is root over of 2 by a is a normalization constant to sine n pi x by a. Now this can be your nth state, as the particle is asked to be in the nth state. So this is the nth state. Now the probability has to be found out. So the probability, you can say, that is the, for the particle to be in the nth state, is, we are calling it as p subscript nx, is nothing but your psi nx whole mod squared dx throughout the entire range. Now in the question it is mentioned particularly that you have to only find the probability density between 0 to a by n. So there is a particular range that is given to you. So instead of this whole range, which was anyway going to be only 0 minus a to plus a, because the particle is only confined within that space and otherwise it cannot exist, but the question asks to be found out from 0 to a by n. So the probability density is independent of the range, so that remains the same, only the limit of the integration changes and becomes like this. And so psi n x whole mod square is basically 2 by a sine squared n pi x by a dx, right? So this is equal to 2 by a. So one thing I think we are forgetting here is that the particle in a box problem is similar about here, but here the box size is not a but 2a. So if the box size is 2a, then something changes. So here this was the common form defined for x equal to when the box size is a, but here because the box size is 2a, so wherever you had a, you will be replacing it by 2a. So now the entire form modifies a little bit. So this is 1 by root over of a sine n by x by 2a. So this thing becomes not, the whole square becomes only 1 by a sine square n by x by 2a. Now as I explained to you in the earlier problem, whenever you have this sine square and you take the entire integral of it, so the simple answer of sine square integral will be, you have to take the upper limit of the integral and divide it by 2. So in this case you have I think there is a mistake over here, so not a by 2n. So okay, so there is a problem in this case. So here the problem would have been just the way I was solving it if the box size was only a, like we usually do, but because here the box size is 2a, you have to obviously replace a by 2a everywhere. So it basically makes the wave function as root over of 1 by a sine n by x by 2a. Now this thing has to be taken in the integral, so this is 1 by a sine square n by x by 2a. Now you can either directly use the knowledge that whenever sine square dx is some integral is happening and you have known the upper limit, so you take the upper limit by 2, so this is a by 2n, and in this case you get 1 by 2n as the probability. You can also check whether this is correct by deconstructing the sine squared some argument as 1 half into 1 minus cos to that argument, let's say y, and then take the integral, and then you can also see that you get back this term only, and this is the ultimate probability value. But in the option that question it is asked that whether the probability is 1 by n and whether 1 by n was true or not. So the answer that was given to it was 1 by n was true, but that is actually only correct That would only be correct if the question had asked that the potential was not from 0 to from minus a to plus a, but from 0 to a. So v equal to 0 from x 0 to a. Then the probability of the particle being trapped in 0 to n, 0 to a by n, is 1 by n. But if the potential is like that it is 0 from minus a to plus a, that means the box size is entirely 2a, then the probability of particle being from 0 to a by n will be not 1 by n but 1 by 2n. Because why? Because just like it is probably to be trapped in the one side of 0 or the positive side of 0, it has equal probability of being just on the other side of 0, that means from minus a by n to 0. That is why earlier what the probability was, now your probability will be half of that. So in that sense it is true what we are getting, even if it is contrary to the solution given provided by them. But actually I think there is a mistake. But the idea is that whether or not the question and the solution given to us matches, but the answer is 1 by n, as the probability for the particle being trapped from 0 to a by n will be false given the potential is given on this form. So in this case our probability answer will be 1 by 2n and not 1 by n. And I also gave you the physical reason why that makes sense, because now you have both sides of 0 to for the particle to be at, so the probability of earlier will be half. Now in this present case this is false is the answer. Now question number 4 is an electron is confined in the ground state of one-dimensional harmonic oscillator such that the uncertainty of position is delta x 10 to the power minus 10 meter. If the expectation value of kinetic and potential energy are same, then the energy required to excite the electron to its first excited state is what amount of electron volt. So basically you have information about delta x position and uncertainty. You have information that the expectation value of kinetic and potential energy is equal, and you have information that it is a ground state of one dimension oscillator, harmonic oscillator problem that energies will be dealing with, and you have to guess or you have to determine what is the energy required to excite it from ground state to first excited state. So let us go back to solving it. So question number 4 is a 1D harmonic oscillator problem, and you know the energy level generic form for this case is En equal to n plus half h cut omega. Okay, where omega is the angular frequency, h cut is h by 2 pi, En is the nth state energy, allowed energy, n is the quantum number here where this can take discrete values like 0, 1, 2, dot, dot. So for n equal to 0 the particle is in ground state or GS, where E0 is equal to just half h cut omega. But for n equal to 1 it is the first excited state, and that we state by E1 of the first excited state energy, that is 1 plus half h cut omega or 3 by 2 h cut omega. Now what will be the energy it has to acquire to jump from ground state to first excited state is delta E equal to E1 minus E0, that is 3 by 2 h cut omega minus half h cut omega, that is only h cut omega. Energy required, that is the thing that they have asked to calculate. Energy to jump from ground state to first excited state. Now what other information we have is that the position uncertainty for this case is 10 to the power of minus 10 meter. Now once you know the position uncertainty, what informations can you get out of here? So to calculate this thing, you know that h cut is an universal constant, that value will be known, but you do not know what omega value is. So you have to answer that first. So another information is that the expectation value of kinetic and potential energy are equal at ground state. That is where the particle was initially at. So that net energy expectation value, which is a summation of kinetic and potential, is nothing but 2 times this thing, right? And or you can also say this is 2 times potential energy. So you know that for harmonic oscillator problem the potential has this form that it is half m omega squared x squared. So this is the potential energy for a harmonic oscillator problem. You can easily guess it by, like, you can define m omega squared as your k, and then it simply becomes half kx square, which is the typical potential energy form of a spring with a spring constant of k. Only thing is that here it is harmonic oscillator, so instead of k we have m omega squared. So there we have omega, right? So since you know this, so you can express the E net as 2 times half m omega squared x squared, right? So this is simply the total energy, because kinetic and potential parts are just same, and don't forget that expectation value. So this is the average sort of a thing that we are doing, and because m omega square is constant, it is taken out, and only x squared average is there. This is the net energy in for the particle at ground state. Now because you know ground state energy already, the energy allowed for ground state is only known as, from the quantum mechanical form of the harmonic oscillator energy levels, is half h cut omega, and this is to be equal to E net that we got from here. So we have half h cut omega is equal to m omega squared x squared average. So from here we'll know what is omega. So omega is basically this omega cancels out. So this is h cut by 2m x squared average. Now you know omega, you can directly get the energy to be for the particle to be excited from ground state to fast excited state is h cut omega. So you have to just replace omega here, but it is still not done, because x squared average you do not know. You only know what is delta x, but this is not known, right? So from there you can get that what is delta x. Basically delta x is nothing but root mean square deviation. So this is like a standard deviation thing. So you have x, the original variable, and you know its mean value of x. Let's say x expectation value or average value of x is this bracket x, and root mean square deviation means, so this whole term is a deviation of each possible value of x from the mean value of x, right? And this is a root mean square deviation means deviation whole squared and then its square root, like that. So then if you deconstruct it, so this is x squared minus 2x x average plus x average whole square. So what you have here is that you do not need to even go to this part. You can directly straightforwardly put from here that specifically you know that the average or mean value of x is 0 for a problem of harmonic oscillator case, right? So if exact expectation value, we can go back to the harmonic oscillator like discussion of this course, and you can find out why I am saying this, but this is a given known information to you. And if that is so, then it is just x minus 0 whole squared, right? So this is simply root over of, sorry, root mean square deviation. So you also had to take a mean out of this, root mean squared. So this is basically that. So you have to also take this one, right? There is a some average sign over here, and this part is discarded, and this thing. So this part is 0 because for harmonic oscillator this is 0, but the what it leaves behind is, sorry, let me redefine this whole formulation because this is getting messy. So what I am trying to say is that this is the definition of delta x uncertainty is basically square root of x minus x average, this thing's whole square, and then an expectation value. So this is root mean square deviation. So this is deviation, and sequentially root mean square deviation. So deviation and then going back is square. Then this is the mean, and this is the root. So that's how I memorize it because it gets confusing to me. So this is RMS deviation or root mean square deviation. Means first of all there is a deviation from x to x expectation value, then you take a square of that, then you take a mean of that, and then finally take the square root. So this whole thing is basically x. Now for harmonic oscillator case, because already x average is 0, you can directly put it here as 0, then this whole square, and then this average. So this is nothing but simply x squared average. So x squared average square root is delta x, then x squared average is actually delta x whole square, which is 10 to the power of minus 20 meter square in SI units. Now going back to the problem, that the energy to excited first excited state, that is n equal to 0 to n equal to 1, is h cut omega, where h cut value is known to us as universal constant 1.05 into 10 to the power minus 34 joule second. Okay, sorry, first of all let me put down the value of omega. So this is h cut by 2m x squared average. So this is h cut by h cut 2m x squared average. This is h cut squared by 2m x squared average. So because this is h cut squared, so this is this thing whole squared into 1 by 2 into electrons mass is 9.1 into 10 to the power minus 31. So you have to take all that terms in SI units and then convert. So and this x squared average is now 10 to the power of minus 20. So you have, when you calculate this using your calculator, you will get this is equal to some 6.057 into 10 to the power of minus 19 joule, and to convert into electron volt you have to divide by 1.6 into 10 to the power of minus 19 joule per electron volt. It's a conversion factor, so that will give you 3.79 electron volt as an answer. So this energy required is 3.79. So our answer here will be 3.79 electron volt, and you see the answer is between 3 to 4. That is, our answer is correct. Now question number 5 is let psi naught and psi 2 denote respectively the ground state and the second excited state energy in functions of a particle moving in harmonic oscillator potential with frequency omega. So it is n equal to 0 state, this is n equal to second 2 state. So this is ground state and second excited state. Now at time equal to 0, the particle has the wave function of this form. Then the expectation value of energy as a function of time can be written as what? So this is a wave function that is given to you, and you have to find out the energy expectation value, right? So energy expectation value, how do you get expectation value of an operator in quantum mechanics? So that is what information we'll be using out here, how to get the expectation value of terms. So yeah, so first of all let me choose a page and then start. This is question number 5. So I can tell you an easy trick, and then I will finally tell you an easy trick, and first I will derive it fully for you. So you have to take the expectation value of energy. So this is the expectation value sign, like this bracket on this energy term. So first of all, the idea of expectation value in quantum mechanics is that you have to find out the wave function or eigenfunction for this case, and you have to operate that operator on that. Let's say in this case, let's say energy means it is the Hamiltonian operator, right? So Hamiltonian operator gives you the eigenvalue as energy. That means the corresponding operator to find out energy in quantum mechanics is h cap or Hamiltonian. So that operator has to operate on the given wave function psi for this particle, and then it has to be sandwiched with another psi like this. This is the bracket notation. I don't know if you are already familiar with that. If not, let us take the other way, that you can simply think of it like this is like, how to say, this is like, yeah, this is like psi star x, then h cap, this operator acting on psi x dx from the entire limit of minus infinity to plus infinity, right? So in this case, because it is a harmonic oscillator problem, so you know the Schrodinger's equation is that H psi is equal to I H cut del psi del t, right? And also, so this is a time dependent Schrodinger equation. So the right hand side has derivative with respect to t. So from here you get the Hamiltonian operator form as I H cut del t, because that is the whole thing operating on psi. And also for the eigenvalue form of it, eigenform of this Hamiltonian operator is simply H cap psi is equal to E psi, right? So from here the operator is coming as H cap. So basically here you put psi star into H cap psi is already we have got I H cut del psi del t to dx, because it is from x minus infinity to plus infinity. Now the psi x form is given to you. Psi xt, basically psi xt is equal to 1 by root over 3 psi naught x, only the x dependent part, e to the power of minus I e naught t by h cut plus root over of 2 by 3 psi 2 x e to the power of minus I e 2 t by h cut. So del psi del t is, you take the derivative with respect to t, 1 by root over t 3 psi naught x is only x dependent, so no effect of the derivative with respect to t. Only this is minus I e naught by h cut e to the power of minus I e naught t by h cut plus root over 2 by 3 psi 2 x minus I e 2 by h cut e to the power of minus I e 2 t by h cut. Right, so once you have this, then again go back this step. This is integral of psi star x. Remember, this is the entire psi. So psi star x and I h cut del psi del t dx. Now del psi del t you have to replace, and psi star x you have to replace by taking a complex conjugate of this form. Clear? So you do this one by one. So this is the integral sign. Psi star x is simply 1 by root over 3 psi naught e to the power of, instead of minus, this is plus I e naught t by h cut plus root over of 2 by 3 psi 2 e to the power of plus I e 2 t by h cut. And then this I h cut is constant, so it comes out I h cut. Then del psi del t, simply this whole term you have to put 1 by root over 3 psi naught. Then minus I by h cut is common out here, so minus I by h cut. Then e naught to the power of minus e naught t by h cut plus root over of 2 by 3 psi 2 e2 e to the power of minus e2 t by h cut, then dx. So this I h cut and minus I by h cut, minus I square is plus 1, so this is plus 1 as a constant outside. Now in the integral, if you take term by term this multiplication, so you'll see that first term and this term is 1 by 3 psi naught. So this is psi naught star, because it is a complex conjugate, I forgot. So this is psi naught star psi 2 star, and this is psi naught psi 2. So this term multiplied with this term will give you psi naught whole mod squared, and e to the power of this thing and this thing cancels out, because e to the power 0 is 1, and the extra form is e naught. So this is 1/3 psi naught square e naught, okay, plus this term and this term when you multiply, this is 2 by 3 psi 2 whole mod squared. Similarly this thing and this thing cancels out, and you get only e2, right? Plus the other terms are cross terms, I mean 1 by root over 3 into root over 2 by 3 psi naught star psi 2 e2 e to the power of plus I t by h cut e naught minus e2. Similarly cross term of this to this is root over of 2 by 3 into 1 by root over 3 into psi 2 star psi naught e to the power of also e naught to the power of plus I t by h cut e2 minus e naught. This whole thing to dx, right? So because you see that this last two terms will give you 0 because you have psi naught star psi 2 dx or psi 2 star psi naught dx. So all of them will be 0 because they are from different eigenfunctions. So the cross terms product integral will be 0. Only psi naught whole mod square dx equal to 1 or psi 2 whole mod square dx equal to 1. Otherwise these are 0. So you are only left with these terms, that this is plus 1. So this cancels. This is not taken. So this is 1/3 psi whole mod square dx is giving you 1 because all other terms are independent of dx, right? So this is into 1 plus also 2/3 e2 as a constant comes out, and psi 2 whole mod square dx is 1. So what you get is e naught to 1/3 plus 2/3 into e2. So this is the final energy expectation value for this kind of case. But now I'll tell you the shorter trick. It's a very simple trick that whenever you have the wave function mentioned like this, right, and you know that individual coefficients coming from them. So like here there is an e1 e naught and there is an e2, and you have these individual coefficient terms. So to get quickly the answer to energy expectation value is taking each of these coefficients and take the whole squared, like 1/3 square, and multiplied by that particular term's energy eigenvalue. That means E naught plus the other term coefficient root over 2 by 3 whole squared into their expect energy eigenvalue, that is E1. So basically what you get is 1/3 E naught plus 2/3 E1. So just check that this is exactly the answer you have calculated below from all this calculation. So this is the simplest easy trick, easy and quick trick to solve such problems when you have MCQ type and you need to solve them in a shorter time. Then it is the answer, but you also have to know how that is coming. So I have derived the whole thing for you, and so the final answer will be, I have not yet written down the final form, so it was 1/3 E naught plus 2/3 E1. And for harmonic oscillator case, you know that E naught is n equal to 0, so it is half h cut omega, and it was not E1, this is E2. E2 is 2 plus half h cut omega, that means 5 by 2 h cut omega. So this is h cut omega common. This is 6, 1 plus 10. So this is 1/3, 2/3 and 2 plus half. So 5 by 2 h cut omega. So why is it not matched? Am I making a mistake anywhere? Because the harmonic oscillator problem, so En equal to n plus half h cut omega. This half h cut omega, and this is 2 plus half, right? So 2 plus half is, oh sorry, I am looking at another problem, is it? Yeah, no, alright. So this was the time independent part of the wave function. That is why there is no t out of here. But you know that how that e to the power minus iet by h cut factor comes whenever you include the time dependence. Because there are these two different eigenfunctions, so their eigenvalues will be different. So in each of the terms, if you include a t, in each of the terms you have minus I naught t by h cut, and separately on the second term e to the power of minus I e2 t by h cut. But anyways, this is 2 plus half, that is 5 by 2 h cut omega. That means if you take h cut omega common, then this is 1/3 into 1/2 is 1/6 plus 10 by 6. This is 11 by 6 h cut omega. Okay, and somehow we are not getting that. I think the answer options are not correct here, but this is the final answer that you will get out of here. So okay, right, this is done. And then question number 6 is the probability density for a particle to lie between x and x plus dx, which is in a state psi x equal to this plus this, will be how much? So the probability density you have to calculate, that means jx basically, right, not the integral of that, and psi x is given to you. So basically you know, so let us solve it right here. So number 6 is basically jx probability density is mod of psi x whole mod square, and you know psi x, this is psi star psi, right? Sometimes the star may not be clear, just bear with that. And so this is psi star psi is a star e to the power of minus I px by h cut plus b star e to the power of plus I px by h cut. Because they have not mentioned whether a and b are real, so I am taking it as a complex, so I am taking a star and b star. And psi x is simply a to the power of plus I px by h cut plus b to the power of minus I px by h cut. So you multiply, the first term is whole mod a whole mod square e to the power 0 1 because they cancel out, and then a star b e to the power of minus 2I p by h cut plus b star a e to the power of plus 2I p by h cut plus b whole mod square, and this term cancels out. So this is a whole mod squared plus b whole mod squared plus, if you think of it like this is only the magnitude, a whole mod b whole mod, then the second part also has a whole mod and b whole mod, so they can take them as common. So this is e to the power of I into 2p by h cut plus e to the power of minus I into 2p by h cut. And because you know this is a similar form, e to the power of I theta plus e to the power of minus I theta by 2 is equal to cos theta, right? So this is, so you have to half this, that means you have to compensate with the product of 2, right? Sorry. So this thing becomes a whole mod squared plus b whole mod squared plus 2ab cos 2p, sorry I missed a x here, so this is x 2px by h cut. So this is your final answer, and you can see that this answer matches with option A, so this is correct. Now question 7 is that for a potential barrier of height u0 and finite width b, the position space wave function psi x will be oscillatory for any x if and only if the energy of the particle is either greater than 0 or less than 0 or negative. That you have to find out. So there is a general equation for this kind of scenario, is that you have just simply mentioned, it is simply mentioned that there is a potential barrier, that potential barrier is of height u0 and the width of the barrier is b. So the particle is coming, it can either have an energy, so let us hypothetically draw the energy level of the incoming particle is like this. So this is, the red dot is the energy level, and clearly it is below u0 because it is inside this potential barrier. It can also be like this, where it is above u0, that is above this potential barrier, but this potential barrier is there, and there are options whether E can even be 0. But let us, for simplicity, let us only choose these two conditions, that whether E is greater than u0 or less than u0. So for this kind of case, you divide it into regions, right? So this is, let's say, region 1, this is region 2, region 3. For now we are only concerned about region 2. So let us write down the Schrödinger's equation there. So let us think that the particle is going, and the wave function of the particle in region 2 is psi 2. Psi 2x is the particle wave function within this potential barrier. So this is minus h cut squared by twice m d2 psi 2 by dx2 plus vx psi 2x equal to e psi 2x for this case. Now E is the energy of the particle which can be either greater than or less than U naught, and Vx for this case is defined as U naught of the potential barrier within this region, because here the V is constant, not a function of x, and this constant is U naught. So this is d2 psi dx2, and then you take the whole thing above. So this is minus 2m by h cut squared U naught psi 2 2m basically you are taking the whole thing to the other side, so this minus sign goes plus, this plus goes minus, and plus remains plus. So the right hand side you take everything up to E psi 2 is equal to 0. Then you have d2 psi 2 by dx2 plus 2m e minus u naught by h cut square psi 2 equal to 0. Now we redefine this term as k. So k equal to root over of 2m e minus u naught by h cut square, giving you h cut only. So for this case you have to think what is the conditions that we have here. So condition 1 is that E is greater than U naught. That means it's above the potential. That means K will be here 0 as for the form of K. So K is greater than 0, that means d2 psi by dx2 plus, this is K squared, right? So K squared psi 2 equal to 0. So now for K to be actually real and valid, so this thing has to be greater than 0, because otherwise there is a minus sign on below the square root sign, then K becomes not real, K becomes imaginary, and we don't want that. So we take K is real, not K greater than 0. K is real when E is greater than U naught. So for a real K, this is d2 psi dx2 plus k square psi 2 equal to 0. This is straightforward the harmonic oscillator type of a equation, right? And the solution is also known to us, that d2 psi dx2 equal to minus k square psi equal to I of k whole squared into psi, because minus comes from I squared, so that is why we have taken it in a closed I squared I k whole squared form, and this is simply psi 2x equal to a1 e to the power of plus ikx, this thing, plus a2 e to the power of minus ikx. So you know that e to the power ix plus e to the power minus ix, this combination gives you sine and cos x. So somehow if you divide and disintegrate these parts, you will take a sine term and you will get another cosine term. So this can be a cos x plus a2 prime sin x. These are oscillatory solutions, right? So oscillatory because sine and cosine are oscillatory solutions. So you get your answer that you get an oscillatory solution to this problem whenever you have this energy greater than U naught. But let us not leave the whole E less than U naught condition as well, because that can be another question that you might face in some other assignment. So for E less than U naught, and for then you redefine this 2m U naught minus E by h cut square root, this thing equal to k prime, and k prime is real here again because this U naught is greater than E, so k prime is real, but in this case this comes to the other side of the minus equal to sign. So this is d2 psi 2 dx2 equal to, this is basically minus, so minus of that it is simply k prime squared psi 2. So instead of I k squared you have k prime squared, so basically psi 2 x equal to then a3 to the power of kx, k prime x basically, plus a4 to the power of minus k prime x. This is an exponentially increasing and summation with the exponential decreasing solutions. This cannot be called as oscillatory. So this is only for when E is less than the potential. Otherwise, if E is greater than the potential, you will get an oscillatory solution. So this is the correct answer. Okay, now question number 8 is 1 electron volt in electron got trapped inside the surface of a metal. If the potential barrier is 4 electron volt and the width of the barrier is 2 angstrom, then the transmission coefficient T is what? Now, I will not solve you the entire problem to get to the formula, because this is a very well-known formula and well-known problem of the potential barrier, right? So I'll be directly using that, and you follow the formula from the lecture content. So basically not much, but the boundary conditions and quantum mechanical Schrödinger's equation has to be solved in such cases when you have a potential barrier. In this case, you can divide it at regimes 1, 2 and 3. This is within the barrier, where from x equal to 0 to x equal to b is the width of the barrier, and the height of the barrier is v naught. So everywhere inside the barrier there is a potential of v naught. The particle oscillating is coming. Inside that will be decaying exponential, and then outside there will be a smaller frequency particle going out. So like that. So from here one can take components like the particle coming, particle being reflected, particle being transmitted, right? So in the question it is asked that what is the transmission probability or transmission coefficient something, right? So if this is a1 e to the power of I kx, the plane wave, then the reflected component can be a2 e to the power of minus I kx. So because it is a minus x over here, so that means it is reflected back, and inside that it will be e to the power of minus gamma x, sort of a exponentially decaying thing, right? b1, let's say, and outside it will be c1 e to the power of I k prime x on the other side. But here k and k prime will be same, because they are both in the zero in the this regime that are similar to each other, right? So the idea of potential barrier is that only here the potential is v naught, everywhere outside the v is 0, right? There will be free particle wave like solution. So by that matter, when you take the transmission coefficient dot t, that is simply what is reflected, that's amplitude whole square, by what is incident, a1 whole mod square. Now this will be, there is a formula that you can follow from that book or from the lecture notes, is that t equal to, in short I will directly go to the formula, 16e v naught minus e by v naught squared e to the power of minus 2 gamma l, where gamma is this thing, that 2m v naught minus e by h car. Okay, so you have all the information. You have known what is v naught, the trapping potential. V naught for the electron on the metal is 4 electron volt, and you know what is the energy of the electron, E is equal to 1 electron volt, and you know the size of this whole potential barrier, which is L to the power 2 into 10 to the power minus 10 meter. So you put all of them together, so 16 into 1 into 4 minus 1 divided by 4 squared into the power of minus 2 into root over of 2 into 9.1 into the power of minus 31 divided by h cut is 1.05 e to the power minus 34. This is m into v by e is again 4 minus 1, and then L outside is 2 into 10 to the power of minus 10. So this whole thing takes you to the answer that this is 0.085. So the transmission coefficient of probability is 0.085. So the transmission probability, not probability but transmission coefficient. That means how much is the amplitude square of the transmitted divided by the amplitude square of the incident component. So you get this answer. Question 9 is, consider a potential step of this form where b is equal to 0 for x less than 0 and it is v naught for x greater than equal to 0. The beam of particle with energy E approaches this potential from left. Then the statement that best describes the reflection coefficient R is what? So basically again this is a region wise divide and Schrodinger equation solve and apply boundary condition sort of problem. It is called a potential state problem. So we will be drawing a state potential. So this is the step. Here v equal to 0 and in here v equal to v naught, and this continues till infinity. It is not stopped anywhere like the potential barrier because it is a potential step, and this happens, the stepping up happens at x equal to 0. So you can call this as region 1 and call this as region 2, and this is for x less than 0 and this is for x greater than 0. So you get the incident wave as a to the power of k1x and back as b to the power of minus I k1x, and this thing that comes inside is c e to the power of minus k2x. k2 is the coefficient in for that thing, and it's exponentially decaying because it is inside this never ending potential step. So now by using Schrodinger equation in regime 2, you have d2 psi dx2 equal to k2 square psi, where k2 is 2m v naught minus e by h cut. So then psi x equal to c to the power of minus k2x, and for regime 1 you get d2 psi by dx2 plus k1 square psi equal to 0. So this is psi 2 in the regime 2 and psi 1 in the regime 1. So from here psi 1x equal to a to the power of I k1x plus b to the power of minus I k1x. So these are the two solutions. Now you have to apply the boundary conditions, right? So boundary conditions, where the boundary is at x equal to 0, where the state potential begins, is that psi is continuous at the boundary. That means psi on one side, that is psi 1, is equal to psi on the other side, that is psi 2 at this case. And the derivative also has to be continuous. That means d psi 1 dx at x equal to 0 is d psi 2 dx at x equal to 0. So this tells you that this is a to the power 0 is 1 plus b to the power 0 is 1 plus c to the power 0 is 1 again. So a plus b equal to c. But here this is a I k1 to the power of I k1x plus I k1b to the power of I k1x at x equal to 0 equal to minus c k2 to the power of minus k2x. Now you put the value at x equal to 0. So I k1a plus I k1b, because to the power 0 is 1. This is equal to also at x equal to 0. So this is minus c k2. So from here you get that your I k1 now you can get your c value from here, that c equal to a plus b. So I k1a plus I k1b equal to minus k2 a plus b. So you take one side, I k1 plus k2 a equal to minus k2 plus I k1 b. So b by a equal to I k1 plus k2 below. This is minus I k1 by k2. So this is giving you -1. So the deflection coefficient is nothing but b whole mod square, that is a component coefficient that is reflecting back or coming back, by the independent incident components whole mod square, that is a whole mod square. This is -1 whole mod square, that is +1. So reflection coefficient is 1, totally reflective, when E is less than V naught, right? And what was the question answer options? Let us check. That R equal to 1 when E less than V naught, and R is non-zero if E greater than V naught. So obviously if R is 1 if E less than V naught, but if E is greater than V naught, right? So if E is greater than V naught, then instead of the exponential solution you would get an oscillatory solution inside that potential step. So if instead E was greater than V naught, then in regime 2 psi 2 will be like C to the power of plus I k2 x, and there will be no minus I k2 x because returning component is not allowed in that regime. So everything is going to the right. So in that case, again boundary condition gives you A plus B equal to C, but this thing will become I k1A plus I k1B, I k1A plus B, and the derivative on that is I k2 C, because this e to the power 0 will be equal to 1. So from there you will get that I k1 A plus B equal to I k2 A plus B, and then you get, yeah, what is the other case? I k2 C e to the power of I k2 x. So this is sorry, I missed that minus sign everywhere. That is why it is a problem, because whenever you are taking a derivative, this b had minus I k1 x. So this is minus sign. So minus sign, this is a minus sign. I k1 plus k2 and I k1 minus k2. So this is I k1 plus k2 and I k1 minus k2. So if this you take the whole mod square, then this is not this thing, but I k1 plus k2 whole mod squared divided by I k1 minus k2 whole mod squared. This is k1 squared plus k2 squared divided by k1 squared plus k2 squared. This is equal to 1 when E is greater than V naught. But in this case, because this derivative has a minus b, so I k1 a minus b equal to I k2 a plus b. So I k1 minus k2 a equal to I k2 plus k1 into b. So b by a equal to k1 minus k2 by k1 plus k2. So naturally r equal to b whole mod square by a whole mod square, and it is simply k1 minus k2 whole square by k1 plus k2 whole square. So these two are not same, that this is not equal to 1. So this is a finite value for E greater than V naught. So this is the other part of the answer. So we choose the correct option as this. R is non-zero if E greater than V naught and 1 if E less than V naught. Then the final question is, for an infinite square wheel potential, if the width of the well decreases, let's say the width of the well is A and A is decreasing, what happens to the 0 point energy E naught and the momentum uncertainty delta P? First of all, you know the uncertainty relation that delta x into delta p is nearly equal to h cut or h cut by 2. So for a infinite potential well problem, delta x is nearly the size of the box or the well, that is A. So A times delta p, the position uncertainty, is h cut by 2. So delta p goes as h cut by 2a. That means if a decreases, then delta p should increase. That positional uncertainty, when it decreases, so the uncertainty relation says that when the position is getting less uncertain, that means more and more defined, so this it starts like fluctuating its potential more, that is its potential uncertainty increases. That is also can be seen from this mathematical relation. And the 0 point energy E naught means the energy for n equal to the ground state basically. So for infinite potential well, the ground state is for n equal to 1, unlike n equal to 0 for harmonic oscillator case. So don't get confused by that. So here it is n square pi square h cut squared by 2m a squared, and this is simply inversely proportional to a. So if a decreases, then the 0 point energy should also increase. So both of them increases if you have the decrease in a. So both increase. So with this we have solved the 10 questions for this week, and we will solve the next week's problem in the next week.